Okay, so good morning. This is college algebra. A couple of really quick announcements. WebAssign homework is due today. You have sections 3.3 and 3.5 are due today. That was an extension from Sunday, and so you had a few extra days to finish that up. And then 4.1 and 5.1 homework is due on the 26th, which is next Monday. So that's I did give you an extra day on that one from what I originally had on the calendar. So pay attention to those due dates and try to get that homework done before next Monday also. After this week, after today's lecture, we have 2 weeks of school left, and then it's spring break. There will be no lecture over spring break, but I will give you some times when I will be around to either answer emails or to possibly make an appointment to meet with you in the WebEx room sometime over spring break. So I'll be around over spring break, and so if you have any times over spring break that you want to get together, that would be fine. And then your exam window opens the week after spring break. One advantage to the way that the exam window coming after spring break is that I will be posting the review for exam 2 before spring break. So you'll have a good solid 2 weeks that you'll have that review in your hands before the exam comes around. So that will hopefully help some of you as you try to prepare for the second exam. All right, so today what we're going to do is we're going to finish up our discussion of quadratic functions, talk about completing the square to find the vertex of a quadratic function, and also talk about finding intercepts and zeros, and talk about what a zero is for a quadratic function. And then we will move on into section 5.2 and 5.3 and start talking about polynomial functions with a degree bigger than 2 and start looking at some key features of polynomial functions, including end behavior, the leading coefficient test, turning points, and zeros and x-intercepts. Now, it sounds complicated. I understand that, but remember, we haven't talked about it yet. And when we get to it, my experience has been that Chapter 5 is usually a chapter that students do relatively well on. So just be patient as we go through this, and you'll get the hang of things with polynomial functions as we do that, as we get into that. All right, so quadratic functions is our first stop here. And so remember that the general form for a quadratic function is that it's a function that looks like this. F of x equals ax squared plus bx plus c, like that. This is a second degree polynomial function, right? Second degree polynomial. All right, and then we have a standard form that we identified last time. And the standard form is a form where if the function happens to be written in this form, then you can go ahead and write the vertex for the function because all right, Jennifer, by the way, I just got your chat message, so thank you for that. And absolutely, if you have a question, don't hesitate to send me a chat message. I appreciate that. All right, so a quadratic function in standard form, because we can identify the shifts of the quadratic of the parabola, we can identify that the vertex is going to be at hk, whatever the h and k values are. And so the way to think of that with the vertex is just to think about it in terms of shifts, right? All right. So today what we're going to do is add a few extra things that I'm going to ask you to find with quadratic functions, and we're going to look at more problems, more examples that involve completing the square, because we really only got one of those done last time, and we need to look at probably a little bit messier problems, quite honestly, and because they can get to be kind of messy with the arithmetic. So I wanted to work through one or two of those so you could see how that worked out. All right, so first of all, don't forget, if you have a quadratic, let's say this is our function right here, and it's in standard form. So let's say we have 2 times x minus 1 squared minus 8. But because it's in standard form, you can identify the shifts, and there's some information about this quadratic that you get right away. Right? Since x minus 1 shifts the graph to the right 1, and then minus 8 shifts the graph down 8, we can identify that the vertex for this function is going to be at 1, negative 8. And then you have this vertical line that goes through the vertex that the quadratic, the parabola, has symmetry with respect to this vertical line, and that vertical line is x equals 1. Don't just write 1 there. When you write the axis, write x equals 1 because it is a vertical line, right? And remember, that's a vertical line through the vertex. And so it will always be x equals the x-coordinate of the vertex, all right? Now, that's what we were talking about last time. I would also, I'm going to ask you to find the intercepts, the x and y intercepts for these functions as well. So we're going to start talking about that a little bit. The x-intercepts for this quadratic function, remember how you find an x-intercept is you set y equal to 0. And remember, y is another name for f of x, so you're really talking about where f of x is equal to 0. And for that reason, because you're looking at x values that make f of x equal to 0, those kinds of values are sometimes called the zeros for the function. And so the zeros for a function are simply places where f of x is equal to 0. How do you find the zeros for a function? You set y equal to 0. Right? When you set y equal to 0, you're finding the zeros for the function. Now, one thing you should ask is, well, what's the difference between the zeros for the function and the x-intercepts? Is it just another word for the same thing? And that's actually only partly true because the zeros could possibly be imaginary zeros, right? If the zeros are real zeros, and by the way, there's two categories of real zeros. Those are rational and irrational zeros. And I'm going to tell you what that means. Rational are kinds of zeros that you can write as fractions. So like -3/2 or 1/8 or 8 or 0. Things like that can be written as fractions. Those are rational zeros. And irrational zeros are the ones that have square roots in them, like 1 plus or minus the square root of 2, or plus or minus the square root of 10, or 3 plus or minus the square root of 5 over 2. Things like that, those are irrational zeros. But those are all real numbers. And so when you get a real zero, you get x-intercepts. So if you have real zeros, then you get x-intercepts also, right? And real zeros and x-intercepts then kind of sort of really mean the same thing, right? They're always the same numbers. But you can get another category of zeros, and those are imaginary zeros. And imaginary zeros would be numbers like, plus or minus 3i, or 1 plus or minus 5i over 2, things like that. Numbers that look like that. When you get imaginary zeros, then you have no x-intercepts. By the way, this is important for the rest of the chapter. As we talk about polynomial functions, we're going to categorize zeros. That's going to be important to us, actually. And so this is going to come back to haunt you again as we go through the rest of the chapter. Right? So real zeros give you x-intercepts. Imaginary zeros, no x-intercepts. And then real zeros, we subdivide into rational and irrational zeros. Rational ones are the numbers that are fractions, and irrational ones are the numbers with the radicals in them, square roots, typically. All right, and so that I wanted to kind of clarify how this is going to work for zeros. So I'm going to write x-intercepts down here, but we are talking about finding the zeros for the function. Right, and so what do? We set y equal to 0 in our function, And so you get 0 equals 2 times x minus 1 squared minus 8. Right? And y'all see that what I did is I took f of x and I set it equal to 0 in the original function. Right? Because the original function was f of x equals 2 times x minus 1 squared minus 8. Right? So all I did is plug in 0 where there was an f of x. And now you solve this equation, and you're going to solve this equation using the square root method. You add 8 to both sides of the equation, and then you divide by 2. And then you take the square root of both sides. So you get plus or minus 2 equals x minus 1. And then add 1, and you get 1 plus or minus 2 equals x. And so that gives you x equals 1 plus 2 or 3, or x equals 1 minus 2 or negative 1. And so the zeros for this function, you just list the numbers. If I ask you for the zeros, you list them. It's 3, negative 1. If I ask you for the x-intercepts, then you write the points down, and that would be 3, 0, and negative 1, 0. All right, and then the y-intercepts, or the y-intercept. Remember, we're talking about a function, and so these parabolas can only have one y-intercept. They can't have more than one y-intercept. And functions can only have at most one y-intercept. Now remember, the y-intercept, what you're doing is you're setting x equals 0. So I take my function, which is y equals 2 times x minus 1 squared minus 8, and in place of x, I put 0. So you get y equals 2 times 0 minus 1 squared minus 8. All right, so now 0 minus 1 is negative 1. So you have negative 1 squared like that. But negative 1 squared is 1. So you just get y equals 2 minus 8 or negative 6. And so there's a y-intercept at 0, negative 6. Like that. All right, and so that gives us the information we need then to make a sketch of the graph, right? And then we would sketch the graph. And now that we've got these points, you know, we can take advantage of that, all these points, to make a decent sketch of the graph. You know, so let's see, if we've got in our problem, we are looking at this function, 2 times x minus 1 squared minus 8. We know the vertex is at 1, negative 8. We got x-intercepts at, and let me flip back real quick to make sure, 3, 0, and negative 1, 0. And then we have a y-intercept at 0, negative 6. So that gives us a lot of information and plenty of information to make a decent sketch of this parabola. And let's see, let me move that up a little bit here. All right, so the vertex is at 1, negative 8. So let's see, 2, 4, 6, 8. So here's negative 8's way the heck down here. And so the vertex is sitting down here at 1, negative 8. And then you have x-intercepts at 3, 0, and at negative 1, 0, like that. And then there's a y-intercept at 0, negative 6, like that. And then don't forget that the function has symmetry around this vertical line that passes through the vertex, like that. And, you know, I would use that vertical line there to help me make a decent sketch of the graph, because that means that every point you've plotted here has a mirror image point on the other side of that axis of symmetry, right? And so you get a parabola that kind of looks like this. Not a good sketch at all. Let me redo that. Try to do that a little bit better there. Right, it's a pretty narrow parabola because of the tooth, so that means there's a compression, or I'm sorry, a stretch of the graph. We don't really worry about that too much, but also you may see in WebAssign the author might talk a little bit about a minimum or a maximum value. Because this parabola opens upward, the vertex gives a minimum y value because it's the lowest point on the graph. And so the minimum y value here would be equal to -8 because that's just the y coordinate of that vertex. And so the vertex has a minimum at, or the parabola rather has a minimum at -8 there, at the point 1, -8, where the y value that you get is -8 there. All right. So there's our first kind of work through the whole thing there and add to that the x-intercepts and the y-intercepts that we didn't talk about before. Cynthia, do you have a question?
Yes, I do, Professor. On the x-intercept, I thought we got something else on the page before.
Nope, 3, 0, and -1, 0.
Can you turn the page again? So that's a 3? I thought that was a 2, 0.
No, because remember I got the axis of symmetry in there also. So you know this is at 1, this is at 2, that's at 3 right there.
So no, so when you wrote it next to x-intercept, that says 3, 0.
Oh, that's a 3. Yeah.
Okay, yeah, that threw me off.
Okay, so yeah, I understand.
X-intercept, okay, and then the vertex you knew was -1 and -8 just from looking at the equation.
Yes, because of the way the function was written, I could tell that the shift of the parabola is to the right 1, right? That's a shift to the right 1 right there. And this is a shift down 8 right here. And that shifts the vertex to the point 1, -8.
Okay, and then the y value of the vertex is always the minimum value.
Yes. Well, no. That's actually a good question, but it's a minimum value if the parabola opens upward. But if the parabola opens downward, then it's not a minimum. Then it's a maximum. Right? Because now it's the highest point of the graph, not the lowest point.
Okay.
And we're going to see one like that. So, in fact, we might as well go ahead and do that now. Let me. I'm going to kind of cordon off the page here a little bit. So let's look at another example here. So let's say we have f of x is equal to, and let's look at one that's not in standard form and see how we're going to complete the square to do this problem. So let's say we have -x squared, let's say minus 10x minus 20. All right. See how we can deal with this graph right here. Now, when you have to complete the square, like I said, to put this in standard form. But when you complete the square, the lead coefficient must be 1. The lead coefficient has to be a 1. And I say positive 1, must be positive 1. And see, so in this problem, the lead coefficient is a -1. And so what happens when the lead coefficient is not a positive 1? And so what you have to do is you have to factor out whatever that lead coefficient is, you factor it out of the first two terms. So what I might do is this, is follow these steps. First thing is move that constant over. Always move the constant over as your first step. And then if the leading coefficient is not a positive 1, whatever the leading coefficient is, you have to factor it out of those first two terms. Notice you don't factor it out of the constant, and that's why I slide the constant over as my first step. You leave the constant alone. You don't mess with it. Otherwise, you won't be able to complete the square here. All right, so whatever that leading coefficient is, you factor it out of the first two terms. And then remember, the idea here is you take half the middle coefficient, and square it. And so, and you're going to add it into that blank. So half of 10 is 5, and 5 squared is 25. So I'm going to add 25 in there, right in here like this. Right, so I've added that constant in. Now this is where it gets tricky, because what you also have to do is you have to do the opposite on the outside of the parentheses. And it looks like I've added 25 here, but that negative 1 is being multiplied by everything inside the parentheses. So this negative 1 gets multiplied by this 25 also. And negative 1 times 25 is negative 25. I haven't really added 25 here. I've really subtracted 25. And I know it looks like I've added it, but that negative 1 gets multiplied by every one of those terms. And so to do the opposite right here, when you do the opposite, I'm not subtracting 25. I am now going to add 25 over here. It looks like I'm adding 25 twice. I am not adding 25 twice because the first one's getting multiplied by negative 1. That first 25 is really a negative 25. And so that negative 25 and the positive 25 on the outside would offset each other. They'd balance each other out. So it means I'm not really doing anything to the right side of the equation. All right, so that's tricky. And we're going to definitely look at another example like that. Good morning, Erica.
Hello.
Welcome. All right, and so now we go ahead and factor the trinomial that's in the parentheses. It will always factor, and we talked about this before when we factored using completing the square. It's always the square root of the first term, the sine of the second term, and the square root of the third term. And then that expression is squared. And then on the outside of the parentheses, we've got a plus 5. Negative 20 plus 25 is plus 5. And so now we have enough information all of a sudden to make a sketch of this graph. The vertex, because it's in standard form, the vertex we can identify by the shifts. The x plus 5, remember, shifts the graph to the left. And so this vertex is at negative 5. The plus 5 on the outside shifts the graph up. So the vertex is at negative 5, 5. The axis of symmetry is going to be at x equals negative 5. That negative 1 in the front means that this parabola is going to open down, right? And so keep that in mind as we make the sketch. All right, and now you have to find the, I'm going to also ask you to find the intercepts, right? And so you got to find the x-intercepts. And remember, that means we're also looking at the zeros for the function. And we need to find the y-intercept also. Now let's write the y-intercept down right away, because I want you to think about how you find the y-intercept as you set x equals 0. So go to the original function and look at that original function. And when you substitute 0 in for x, notice that all you're left with is the constant at the end, the negative 20, right? Because you're plugging 0 every place you see an x. And so the y-intercept should be easy in a function like this, because it's always going to be the constant term. And you get 0, negative 20 for the y-intercept. All right, now let's look at the x-intercepts. Now I'll do this off to the side over here. The x-intercepts, remember the zeros, you set y equal to 0. So in the function, you could really do this in the original form, in the general form for the function, or in the standard form that we finished with at the end. You could go either way for finding the x-intercepts. Sometimes it's easier to use the original function. Sometimes it's easier to use the one after we've completed the square. It just depends on the problem. I'm going to do the completing the square form right here. Right? You get the... you substitute 0 for y, and you get 0 equals negative x plus 5 squared plus 5. I'll add the x plus 5 squared to both sides. I just move that to the left side. And you get x plus 5 squared equals 5. Right, just adding it over, moving it over from the right side to the left side. And then take the square root of both sides of the equation. You get x plus 5 equals plus or minus the square root of 5, or x equals negative 5 plus or minus the square root of 5. And so those are the x-intercepts for this function. The x-intercepts, and these are, remember, these are called irrational x-intercepts, but they are x-intercepts. It's negative 5 plus the square root of 5, 0, and negative 5 minus the square root of 5, 0. Now, if you're going to graph those, you're going to need a calculator to make an estimate of what negative 5 plus the square root of 5 and negative 5 minus the square root of 5 is. Square root of 5 is somewhere about 2.25, so I'm just going to kind of ballpark it here. And so the first one is at about negative 7.250. And the second one, negative 5 plus the square root of 5, is at about, it's negative 5 plus 2.25, so that's about 2.75. So 2.750, about. Those are just estimates there. But if you're going to make a sketch of the graph, it would be good to have at least decent estimates where those are. All right, and so then from there, you can make at least a decent sketch of the graph, hopefully. And let's see. So let's go ahead and go to the next page, and we'll just make a quick sketch of the graph. I'm not going to get all the points on here that we need, but we'll at least get some of them. So you have negative 5, 5 is the vertex. So there's negative 5 right there, and then 1, 2, 3, 4, 5. So there's our vertex right there. And then we get x-intercepts at about negative 7.25 and about 2.75. Don't forget that there's an axis of symmetry that goes through the vertex, right, that vertical line. So the graph has symmetry around that line. And so you get negative 7.25 right about there, and 2.75 right about there. And you can see that those points are mirror images around the axis of symmetry. And then beyond that, the y-intercept is too big for me to put on this particular graph because it's at 0, negative 20, so it's pretty far down there. So, but that at least gives me a decent sketch right there. All right, so anybody have any questions about that problem? Are we okay there? Any questions?
No questions.
All right. Let's look at another example. So you have f of x equals, let's say we have 2x squared minus 16x plus 9. All right, and we want to make a sketch of that graph. We want to find the information out that we need for this particular problem. All right, this is not in standard form, so you have to complete the square. So we complete the square to write in standard form. Right, because right now we cannot identify the shifts. All right, so remember the steps. So it's very definite steps here to do this. Move that constant over, slide it over so that you're not tempted to factor anything out of that constant. And then whatever the leading coefficient is, you take that out of the first two terms. Now, I know that there's an x common in the first two terms also. Do not factor out the x because then you're not going to be able to complete the square, right? You won't have a trinomial that you can factor. Just take out the constant. So this is x squared minus 8x right here. And then we close off the parentheses and then put a plus 9 like that. So whatever that leading coefficient is, you take it out of the first two terms. All right, and now we complete the square. So we take half the middle coefficient, which is 4, and then square it, and you get 16. So I'm going to add 16 in right here. And now you have to figure out what to do on the outside of the parentheses to balance the fact that you've added 16. And so remember, you always have to do the opposite. Please be careful here. So take this 2 that I factored out, multiply it by that 16. So 2 times 16 is 32. So I haven't really added 16 in this problem. I've really added 32. And so now what do? You do the opposite over here on the outside of the parentheses to offset the fact that you've added 32 to the right side of the equation, of the function there. And so what do you do over here? You subtract 32. All right, and so what have I done? I've really added 32 and subtracted 32 here. All right, and then you go ahead and factor the trinomial. So the x squared minus 8x plus 16, the square root of the first term is x. The sign of the second term is minus, and the square root of the third term is 4. So it factors x minus 4 squared. And then you have minus 23. Right? And so now we're ready to write down some information. The vertex for this function is at 4, negative 23. All right, the axis of symmetry is going to be at x equals 4. And then we also need to write down the x-intercepts and the y-intercepts. Right, and so the now the y-intercept again should be, the y-intercept should be easy in this kind of problem here, because all you have to do is look at the original function and substitute 0 for x in the original function, the way it was written at the beginning. And so you get 0, 9, because you just get the constant term there. X-intercepts are a little bit more challenging to find. And so what I'm going to do on the x-intercepts here is I'm going to use the first equation rather than the last equation, just to do something different. So you have 0 equals 2x squared minus 16x plus 9. Right, that's the original function. And then you use the quadratic formula to solve that equation. So, so when you use the quadratic formula, you get negative b, so that'd be 16 plus or minus the square root of b squared. And see, right happens, what happens here? You get 16 squared, you go, oh my gosh, the numbers are going to be huge. And then this is times, or minus 4 times 2 times 9. You know, if the numbers get to be too big, then go to the second version of the function. Remember, for the x-intercepts, you either use the original function or you use the one after we've completed the square. You use one of those two forms right there, and you're going to use one of those two forms to find the x-intercepts. And it ultimately doesn't matter. You sometimes get the answer in a slightly different form. Sometimes one of those is much easier than the second one. So in this case, you know, if you use the quadratic formula and you get that the numbers are too big, you know, that might tell you that you go and try the second form there. All right, so I get x equals, I'm going to stick with this, 16 plus or minus the square root of 256 minus 72 over 4. And the numbers are kind of yucky here. And so you get x to be 16 plus or minus the square root of 184 over 4. Right, and right? And then from there, right, you see what you can do. 184, you can actually simplify that, believe it or not, because it's 184 is 4 times 46. So you get 16 plus or minus the square root of 4 times the square root of 46 over 4. Yuck. Or x equals 16 plus or minus 2 square root of 46 over 4. And then you could divide out a 2 there, and you get x to be 8 plus or minus the square root of 46, all divided by 2. And those are the zeros for the function. And if you put them in ordered pair form, then you get the x-intercepts. Now I'm going to try to avoid really gross answers like this, like especially if you're going to have to graph something. So don't get too panicked about having to graph something where the numbers are just awful, because I'll definitely avoid that on a test. So, all right, so that gives you a sense of how you go through completing the square for this kind of problem. And so that's where we're going to stop. And by the way, one thing I didn't mention on the last problem is notice that when the parabola opens downward like this one is, that the vertex gives a maximum y value. Right, so the maximum y value on this problem, maximum y value is at 5. Right, because that's the y coordinate of the vertex. The vertex is at -5, 5 there. So if the parabola opens down, you get a high point or a maximum value for the y value. If the parabola opens upward, you get a minimum value for the y value. All right. Now I'm not going to sketch this one, like I said, because the numbers get kind of big on this last one I did, but you could plot the points and make a decent sketch of this graph on the next problem, or on this problem right here. All right. And so now we are going to go on to polynomial functions where the degree is bigger than 2. So the first thing I want to talk about here, before we do anything else with polynomial functions, and this actually relates back to linear and quadratic functions also, is when you have a function whose graph looks like this one right here. Let's say graph that looks like that one right there. The places, the graph goes from increasing to decreasing and then to increasing again. And the places where the graph shifts from increasing to decreasing or decreasing to increasing, in other words, those high points there and low points on the graph, those are called turning points of the graph. And so this graph has turning points. And one of them is right here at -1, 3. And the other turning point is at 2, 0. Right, that's a place where the graph goes from falling to rising or rising to falling. Right, those are called turning points. And those are high points or low points on the graph of a polynomial function. And so that relates to graphs in this way, to polynomial graphs. It's this fact. We are not going to prove this fact at all, but this is a fact that is true about quadratic or about polynomial functions in general for all polynomial functions, and that is that the graph of any polynomial function can have, let's see, a polynomial function of degree n. I kind of left that part out. Of degree n can have at most n-1 turning points. So that means that the number of turning points at most can be one less than the degree of the function. All right, so I want you to think, first of all, let's go all the way back to linear functions. Linear functions are, remember, are lines. Those functions are first degree polynomial functions, right? F of x equals mx plus b, right? These are first degree polynomial functions. And so what's the most number of turning points that you can get? The most turning points you can get is one less than the degree. So what would that be? It'd be 0 turning points. And that makes sense, doesn't it? Because a linear function, what kind of a graph is a linear function? It's a line. And so lines never turn, do they? Right? There's no turning points in a line at all. Right? So they have 0 turning points. Lines never turn. Right? Lines never have turning points. So that really fits in very well with that fact that I wrote down, right? That polynomial functions of degree n can have at most n minus 1 turning points. All right, so that's linear functions. So now let's look at quadratic functions. See how that rule fits in with quadratic functions. So a quadratic function is a function in the form ax squared plus bx plus c, right? And so its degree is 2. And so what about quadratic functions? They can have at most 1 turning point. But what are the graphs of quadratic functions? The graphs are always parabolas, right? Because it's a quadratic function, are always parabolas. And how many turning points do parabolas have? For all parabolas have exactly 1 turning point. Right, so if you think about a function that looks like this, right, a typical parabola, right, 1 turning point, and that's it, and that's this vertex, right? The vertex is the 1 turning point, right? The vertex is the turning point. It's where the graph goes from either rising to falling, or falling to rising. In this case, this graph goes from rising to falling at the vertex, the one that I just sketched there. So this rule that I wrote down in the previous screen works really well, you can see, for linear and quadratic functions. It fits in perfectly, right? All lines have 0 turning points. Those are first degree polynomial functions. All parabolas that are second degree polynomial functions are all quadratic functions. Their graphs are parabolas. They have just 1 turning point, right? All parabolas just have 1 turning point, and so it fits in really well. So now let's look at other functions, degree higher than 2. So let's look at this function right here. F of x equals 2x cubed minus 3x squared minus 6x plus 8. All right, so the degree, remember, to figure out the degree of a polynomial function, you just pick out the term that has the biggest power of x in it, right? And usually we write that in descending power, so it's usually the first term, but it doesn't have to be. It's just the one with the biggest power. So this polynomial is a degree 3 polynomial, right? Because of that 2x cubed term. And so what can we say about the turning points on this? The graph has at most 2 turning points. It cannot have more than 2 turning points. Now notice it says at most. That's what the rule says. So it could have fewer. And actually what turns out that happens, we will see in a little, either later today or next Monday, is that they either have 2 turning points or they don't have any turning points at all. It's one or the other for a 3rd degree function. All right, f of x equals negative 3x to the 4th minus 6x squared plus 8x minus 1. All right, so this function is a degree 4 polynomial function because of that negative 3x to the 4th term. And so what can we say about the turning points for this graph? The graph has at most 3 turning points. Right? And in fact, what happens is that for a degree 4 polynomial, they're either going to have 3 turning points or 1 turning point. Never 2 or 0. The degree 4 always have either 1 or 3. And for us, the main thing here that we need to know is that they have degree, that they have at most 3. All right, let's see. So f of x equals 1 minus 2x plus x to the 5th. Now notice that function is not written in a typical order. The term with the biggest power of x is in the last term. That's nothing inherently wrong with that. It's usually not written that way, but there's nothing wrong with writing it that way necessarily. This is a degree 5 polynomial, even though the 5th degree term is the last term there. And so in this case, the graph has at most 4 turning points. And you can see that as we progress on with bigger and bigger degrees, the graphs for polynomial functions can get to be more and more complicated because they can have more turning points. Right? The more turning points you get in a polynomial graph, the more complicated the graph can be. All right, so let's see. Let's look at 2 or 3 more examples, but sort of different in some ways. Let's say this next one is f of x equals x minus 2 squared times 2x minus 1 times x plus 3. Now, this function is not written so that you have terms. This is all factors, and so you have to be careful about writing the degree down for a function like this. You have to think about what would happen if I multiplied all these factors out. What would happen if you multiplied all the factors? What would be the biggest power of x that you would get? See, so the x minus 2 squared, you're going to get an x squared in that factor when you multiply that out. And then you're going to get, you have an x, a 2x in this factor, and an x in this factor. And when you multiply those together, you're going to end up with a 2x to the 4th power. So the degree for this function is 4. Right? That'll be a 4th degree polynomial. If I multiplied all those factors out, I'd get a x to the 4th term in there. And so then what can we say? At most, 3 turning points. All right, so I wanted to write down one that looked like that. We will definitely confront that again as we go through the next few days. The next problem, I'm going to actually give you the graph of a polynomial function in this case. And so we're going to talk about how many turning points this graph has. And then talk about the degree that you might get. So here we have a graph of a function So how many turning points does this graph have? Right, that's the question. And so those of you who are listening to me live, what's the answer to that question? How many turning points does that graph have?
3.
Yeah, that's good, Anne-Marie. It has 3. There's a turning point here. That's 1. There's a turning point at the y-intercept right there. That's 2. And then you have another turning point here. That's 3. So it has 3 turning points. And so what's the least degree that this polynomial can be? What's the least degree?
4.
Yeah, good. The least degree is 4. It could be higher than 4, but the smallest degree that you could get for this function is a 4th degree polynomial. All right, so all right, there you go. So if you had a graph, and there'll be some WebAssign questions where they give you a graph and then ask you some information about that graph like that. All right, the next thing we want to talk about, let's look at another graph here. And so let's say our graph looks like this one right here. I'm kind of marking off the turning points for this graph. So let's say we have a graph that, and by the way, this may look like a crazy graph, but easy to write down a polynomial that has a graph that looks like this one. Not hard at all. And so first of all, let's talk about the turning points. And then I'm going to show you something else about this graph also. So how many turning points?
4.
Okay, so let's see. So Anne-Marie said 4, so let's count them. So there's 1, there's 2, there's 3, and there's 4. Very good. So 4 turning points. And so the least degree for this graph would be?
5.
Yeah, good. The least degree would be 5. It has to be at least a degree 5 polynomial. Now the next thing we want to talk about this graph is something else, is the what we call the end behavior of the graph. The end behavior of the graph is, like the name suggests, is what happens on the ends of the graph, not all the stuff in the middle there, but what happens on the ends. So the ends would be what I'm putting in red right here. That's the end behavior of the graph. And notice in one direction you're moving to the right, you're going to the right, and so what's happening here is that x is getting bigger. X is going to infinity as you go to the right. And on the other part, the other direction for the end behavior, right here we're saying we're going to the left, and here x is going to negative infinity. And what's happening to y? What's on the one on the left? Where's the arrow pointing? The arrow is pointing down, and so that means that y is getting to be a bigger and bigger negative number. Y is going to negative infinity. And on the other side, what's happening to the y value? Well, the arrow is pointing up there, so the y value is getting bigger and bigger. So y goes to positive infinity. And so there's a couple of ways you can see this written out. So first of all, moving to the left, you would say that as x goes to negative infinity, y goes to negative infinity. Right? So in other words, as x is going off to the left, the y value is going down. And when you're moving to the right, you're saying as x goes to positive infinity, in other words, you're going to the right here, x goes to positive infinity, that y is going to positive infinity means the graph's going up as you're going off into that direction. And in some cases, I'll let you just get by with doing this, making just a little rough sketch and drawing in the end behavior there. That the end behavior looks like this, right? Rising as you're going off to the right, falling as you're going off to the left, like that. Right, so that's a way of abbreviating that end behavior for that graph. All right, so let's look at another function. Let's talk about the end behavior for the function. So let's say that this is our graph. Let's see, I was putting it in green, so I'll continue to put this in green here. All right, so this is our graph right here. First of all, let's talk about the turning points and kind of go back over that again on this function. So the turning points, how many does it have?
3.
It has 3, that's right. So the least degree for this function is? 4. Good. It has to be at least a 4th degree polynomial. And now let's talk about the end behavior for this function. So the end behavior, as you're moving off to the left, the graph is rising. And as you're moving off to the right, the graph is rising. So the way we would write this is you're moving to the left. So in other words, as x goes to negative infinity, y goes to positive infinity. In other words, y is going up. Y is rising. Sometimes you'll see as you're going off to the left, y is rising. The graph is rising. And then as you move off to the right, that's as x is getting to be a big positive number. It means you're moving off to the right. And what's y doing here? It's also rising. So it's rising to the left and rising to the right. And then if you want to just abbreviate this, you could abbreviate it just by making a little coordinate system here. And you could simply say that the graph is rising this way and rising this way. Now, so we're talking about the end behavior of the function, and there's actually a way to look at the graph of the equation to tell what the end behavior is. Because all polynomial functions basically have end behaviors that look like either the square function or the cube function. All polynomial functions have that kind of end behavior. So if you look at the square function, right, that's just our parabola. That's the square function right there. Right, and what's its end behavior? It's rising as you're going to the left and rising as you're going to the right. Now what could happen is you could have f of x equals negative x squared. And remember what that negative sign does to the graph is it turns it upside down. Right, it's a reflection around the x-axis. And so now the end behavior is falling to the left and falling to the right. All even degree functions look like this, right? One of these two. All even degree polynomial functions have one of these two end behaviors. In other words, it looks like the square function or the reflected square function. All right, and then if you look at the cube function, Right, the cube function has a graph, remember, that looks like this. And so that end behavior is falling to the left and rising to the right, like that. And if you look at f of x equals negative x cubed, that end behavior is just flipped upside down. So remember, the graph of the function is reflected. It looks like that. And so you have that kind of end behavior. Let's see, choose that a little bit better. So that kind of end behavior. So it's either falling to the left and rising to the right, or it's rising to the left and falling to the right, like that. And so we can say all odd degree polynomial functions have one of these two end behaviors. And now, how do you tell which one you have in either case? Well, you look at the leading coefficient, right? In the to the left here, the leading coefficient here is positive, and over here the leading coefficient is negative. I use the letters LC for leading coefficient. And so here the leading coefficient is positive, and here the leading coefficient is negative. So if you take these two things and put them together, right, so here's the degree is even, and here the degree is odd. You can put those two things together, the degree of the function and what the leading coefficient is, and you can decide what the end behavior is for that graph. So let's categorize some. Let's talk about that. So we have this function, f of x equals negative 2x cubed minus 3x plus 8. All right, so to use this leading coefficient test, that's what we're outlining here. It's called the leading coefficient test. Let's first write down the degree of the function. So the degree of this function is, someone?
3.
Good, 3. And what about the leading coefficient? Is the leading coefficient positive or is it negative?
Negative.
Yeah, it's negative. That's the coefficient of the cube term. So that's negative. And so you have an odd degree function with a negative leading coefficient. And so the end behavior, first of all, let's just draw it out. The end behavior would have to look like the cube function, but flipped upside down. So the end behavior would have to look like this. Rising as you're going off to the left, falling as you're going off to the right. Or, in other words, as x goes to negative infinity, y is going to positive infinity, y is going up. And as x goes to positive infinity, in other words, as you're going off to the right, y is going down, like that. All right, so you get some information about the graph immediately based on the degree and the leading coefficient. All right, let's say we have f of x is 3x to the 4th minus 6x squared plus 8. So what's the degree of this function?
4.
Okay, the degree is 4.
6. Oh, sorry.
Do you agree it's 4?
Yeah.
Remember, this is not written in factored form. This is written out with terms. And because it's written out with terms, then you're just picking up the biggest exponent, right? If it's written out with factors, then you have to treat it differently. But with terms, you just pick out the biggest one. So the degree is 4, and what's the leading coefficient? Is it positive or negative?
Positive.
Yeah, you're looking at the 4th degree term, right? That's all you have to look at. And that's kind of like the controlling term of the function when you're looking at the end behavior. And so that's got to be positive. And so what do you have here? You have an even degree function with a positive leading coefficient. So what I do all the time when I see even degree positive leading coefficient, I just think of y equals x squared. Think about the parabola. It's got to have the same end behavior as x squared. So that means, if you think about the way the parabola looks, it's got to be rising as you go to the left, rising as you go to the right. Right? Or you could write it as what? As x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, in other words, off to the right, y is also going up. Right? If the graph's going up, the y values are going to infinity. If the graph is going down, the y value is going to negative infinity. All right, and let's see, we'll finish this discussion with this problem. So let's say we have f of x is x plus 2 times x minus 5 times 2x minus 3 times, and I'll be tricky here, 4 minus x. All right, so notice this function's written out in factored form, so you have to be more careful about the degree. You have to look at the degree of each factor individually and then multiply them together. So what's the degree for this function?
4?
Yes, Charlotte, that's right. It is degree 4. Right? Each one of these is degree 1, and when you multiply 4 degree 1 factors together, you're going to get an x to the 4th in there. So this is degree 4. Now the leading coefficient, this one is tricky. Look at the x's in each term. Look at the x's. That's a positive x. That's a positive x. That's a positive 2x. This is a negative 1x. See, so when you multiply all those x's together, not only do you get an x to the 4th, but you're going to get a negative x to the 4th because of that last one being negative. And so the leading coefficient here is going to be negative. And so you have an even degree function, negative leading coefficient. Think of f of x equals negative x squared. This graph has to have the same end behavior as negative x squared. In other words, the square function flipped upside down. And so the graph has to have an end behavior that is falling as you go to the left and falling as you go to the right. So in other words, as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to negative infinity, right? The graph's going down in both directions there. All right, anybody have any questions at all that they want to ask about?
I'm good.
All right, so now I'm going to just point out the pages in the textbook where you can get problems from each of these sections we've talked about. In section 5.1, this is page 357. Problems really from 7 through 19 and 35 through 45. Those are on quadratic functions. And then in section 5.2, now that we've talked about the leading coefficient test, this is on page 372. Problems really from 13 through 45 would be good practice problems to look at. All right, and so next time we'll start talking about finding zeros. We're kind of through section 5.2. Now, we have talked a little bit about some things out of 5.3, but we'll get into 5.3 and 5.4 in the next class period. So if there are no questions, everybody who's here with me live, you're my regulars. Thank you so much for keeping me company on Monday and Wednesday mornings. Go do some algebra. and have a great day, okay?
You too. Have a good day.
Thank you.